We're still talking about this free energy idea. So all of these things occur in nature. You've seen it. You've seen, oh, maybe you haven't seen it, right? Boiling point elevation. What was that? The people in remember this? Colorado, they used boiling point elevation so they could cook their macaroni, right? The same amount of time it takes us down here to cook it. And what they had to do is they had to elevate the boiling point of water by dumping what in there? Yeah, really anything, any compound, right? Any solute will increase the boiling point. Or any solute will decrease the freezing point depression. So these are all natural processes. Weather, metamorphosis, whatever's going on in biology, all these things that just occur naturally, they can be quantified by this free energy idea. Okay, engines. So we're just going to try to take a little deeper look into this, and how can you use this energy to do work? You know, like we said with the Stirling engine, you can't use all the energy to do work. You don't have 100% efficiency, but you can still use some of this energy available to do work. So what energy is it? It's free energy. These natural processes. It's going to happen sooner or later. Okay, so we don't have rubber bands, but I gave you these little balloons. Now don't stretch them yet, because this isn't going to work if you stretch them first. So let's apply this thermodynamic equation. Delta G equals delta H minus T delta S to the process of a stretched rubber band. Well, stretched balloon. So don't stretch it yet, though. So here's the reaction. We're going to start with a balloon that is stretched, and then we're going to let it be unstretched. And we're going to try to use that equation to predict what the change in entropy was. Because entropy, what the heck, you can't even see it really very often. So what is that number? So let's try to figure it out by just doing this little experiment. So so don't stretch yours yet, because you're going to need it. But here's the reaction, right? This goes to that. So is this process, Audrey, delta G for this process must be what? Positive, negative, or 0? So there's only one question you should ask yourself. Is it spontaneous or not? Is it natural? Here to there. Yes. Yeah, I mean, you can't stop the stretched balloon from not stretching. It's not going to stay this way. So that means delta G has to be negative. Okay, delta G has to be negative for this process. Okay. Okay, now you need to do it. So what I want you to do is kind of feel what this balloon feels like now, and then stretch it and see what it feels like. Right? You got to feel what it feels like now, and then stretch it and see what it feels like. I mean, you can put it on your hand, but my hand can't feel as good as my face can. Then what does it feel? Does it feel like it gets colder or hotter? Hotter. Definitely hotter, right? Feel it before and after. Right? Does everybody agree? So you stretch it. After stretching a rubber band, it feels warm. So stretching a rubber band must be where's all my sheets here? Mix them up a little bit. Kenneth, stretching a rubber band then must be a what process? It feels warm. Exothermic. Stretching a rubber band must be an exothermic process. So if stretching a rubber band is exothermic, contraction, Kendall, must be what? Endothermic. Okay. So contraction on a rubber band is endothermic. So delta H then, Enrique, for a contracting rubber band is positive, because that's endothermic. All right, so let's throw our stuff in here. We want to see what the sign is for delta S. So we said delta G is negative. All right, that's a negative number. This contracting rubber band. Remember, we have products over here, reactants over here. Delta, this is delta G for that reaction. We said delta H is positive for this contracting rubber band. What sign do we put on T? T is always positive because it's what? What unit? Kelvin. So you can never make that guy negative. Delta S must be what then for this to work out? Delta S has to be negative? Because for the math to work out, you've got a positive number minus something, and you better end up with a negative number. If it's 0, then delta G would have to be positive because delta H is positive. See how that's working? You have to subtract. So delta S this must be a what number? Has to be, someone said it, I thought. Positive, right? This has to be positive. If you have a positive times a positive is a positive, right? Times a negative, now it's negative. It must be a big positive number, right? Because it has to overcome delta H. So that means our energy is getting, in this process, energy is getting what? Dispersed, spread out. Well, this is what they're trying to say. They're trying to say that where's the energy at? It's these little crosslinks, these little interactions between the rubber molecules, right? So they get more, here they're more ordered, right? They're more ordered. They're more in line with one another. Now they're just random all over the place, these interactions, right? So let me get my rubber bands back because I don't need them for the next time. Otherwise you guys will just be sitting there snapping each other the whole time. Okay, so yeah, the energy ends up being more dispersed. So upon contraction of our band, the energy becomes more dispersed. We kind of already answered that. So, interpretation of free energy. Okay, let's pick on Connor. When delta G for a process is, then the process can be used to do work. Less than, because it has to be spontaneous. Thank you. It has to be spontaneous. Otherwise, you have to put energy in for that thing to happen, whatever it is. Right? So delta G can equal W. We can't use all that energy to get work, but that's okay. I don't know who's had physics here. Let's see if Mia's had physics. A physicist will say work is what times what. Now work can be anything, but when you're trying to get something done, move an engine or whatever, but move a car. Work is what times what? Distance times force. Force times distance, whatever. Okay. So I'm sitting here applying a force on this chalkboard, Bowdy. Am I doing any work? I'm going to be sweating and everything. If I did this all hour, I'd be sweating and everything. This old man. Am I doing any work though? No, because I'm not going anywhere, right? So there's no work being done. Everything's being dispensed as heat, right? So I guess we're talking about, useful work. We're moving things. Calculating a thermodynamic equilibrium constant. So that's just a concept, not really much to worry about. But now we're getting into it. We're getting into the homework now. We changed the name. This is how we're writing thermodynamic equilibrium constants, K. Well, how did we write it before, Megan?
Concentration of the products of...
Yeah, concentration of products over reactants. But what symbol did we use for equilibrium constants? Wasn't it K?
K something?
K with a little subscript what? And I don't know if we ever wrote this because we got lazy, and I know I did. A C. This is what we were supposed to have been writing this whole time. We're supposed to have been writing KC, but we never did. We always wrote K, products over reactants, and left out what and what? What do we leave out? Out of all equilibrium constant expressions? Solids and liquids, and that little C, right? Yeah. We shouldn't have, but we always left out solids and liquids. Great. So that's not going to change. You still leave out solids and liquids. So in KC expressions, what we did before up to this point, all concentrations, products over reactants, even gases are expressed in units of, what did we use? Enrique, what did we use? We said concentration, but what units of concentration? Moles per liter, but that's too much to write. Just write big M. Right? Molar. So now we've got thermodynamics. So we're supposed to call this a thermodynamic equilibrium constant. Why? Because look, it's down here. It's related to delta G from the tables, right? So this is not Kc, this is K. So what's the big deal here? Well, in thermodynamic equilibrium constant expressions, big K expressions, all concentrations are in units of blank except for something. Cameron. We want all concentrations in units of what except for what? Anyone remember this from the reading? Well, solids and liquids will never be there. They're never in any equilibrium constant expression. So definitely not that one. What's the units for everything? Yeah, all these solutions are going to be in what units for the concentration? It's going to be the same. They want to stick with molarity. They want to stick with molarity. Except for cross out solids and liquids because they never show up. So that pretty much only leaves what? Gases, right? Gases got to be in special units. Jose, you remember reading this? What units for a gas? Here's a hint. Partial pressure. So what are some units of pressure? They're going to pick one of them, and then you got to stick with it. Otherwise, you get all the wrong answers in the tables. What's their convention? Let's guess one. What are some units of pressure? Anyone help them out? There's ATM is one, atmospheres, millimeters of mercury, torr, pounds per square inch. There's several, right? The one that they are sticking with is ATMs. So you just got to, and this is the convention, so we just got to follow it. We have to know it. So partial pressure. How do you calculate partial pressure? Andromeda, do you remember? What was partial pressure? You've got all these gases in a container, and they say, oh, what's the partial pressure of one of these gases? What does that mean? Well, that's osmotic pressure. But you have all these gases in this room, and the pressure due to nitrogen in this room would be its partial pressure, right? So the pressure in this room is a little bit less than 760 millimeters mercury. It's probably like 740 millimeters mercury. And since most of the gas is nitrogen, I would guess the partial pressure of nitrogen is around 720 millimeters of mercury or something. But how could I calculate that? Andrea, how could I calculate that? What's the ideal gas law? What equals what? Get you started. PV equals nRT. All right. So we want to know of gas, I don't know, nitrogen. That's what you're supposed to solve for. P with little n2. Sometimes we had a T on it for total. We want n2. So Cameron, where else would it make sense to put a subscript n2? Anybody help them? N definitely, because N is number of moles, so it definitely makes sense to put a little subscript n2 there. Where else? On the V? I guess the problem with putting on the V is all the gases are in the same container. So that's the same for every gas. Is R the same for every gas? Yep. And T? Yeah, there's an average temperature of all the gases. So what's the partial pressure of a gas in a container? Just use the ideal gas law and put subscripts on the P and the N. Okay. So you need to know the volume of the container. Okay. Yeah, there's the R. What R would, well, we'll worry about that later. That's coming up. The relation between standard Gibbs free energy and the thermodynamic equilibrium constant. Okay, so where do we get this again? This delta G0? Tables, right? Okay. T, they have to give it to you, right? Tell you the temperature. What number are you going to use for R? Now, if you use because there are these different choices for R. Is that coming up down here? There it is. We're talking about this one. Liter atmospheres over moles Kelvin. This is the nice R to use up here, because then it's obvious what to use for all the units for everything, right? But if you do remember the tables, what are the typical units for delta G0? Remember on the top of the table? It was kilojoules per mole, joules per mole, something like that. There's no joule in here. Don't pick this R then. You're going to have a fun time doing converting. I would pick a different R for this equation. I would not use that one for this equation. I would use it up here, but I would not use it for this one. No way. That one's okay. I don't think we've ever used this R. 8.314. What's the unit? Joules per mole Kelvin. This is the one you got to use. So you use this one, you get your answer in joules, right? Because the kelvins are going to cancel. Really, your answer is in joules per mole, because the kelvins would cancel. Make sure T's in Kelvin, and you'll be okay. Okay. So we got that part. Look down here. Connor, we've got delta G0 equation, and then they got another delta G equation, but the little zero disappeared. What's the difference? Oh, isn't this right? What's the difference between these two? Temperature. What does this, I guess what I'm getting at is, why does this, what's going on? What does a little superscript 0 mean? It's going to crash on me. What does a superscript 0 mean? Well, it means you can use the chart, use the tables, but it's only under certain conditions. Enrique, what are they? 1 atmosphere, 25 degrees Celsius. They call it what conditions? Standard. They call it standard conditions. Whenever you see a superscript 0, you're supposed to say standard delta G, standard change in free energy. So that means use the tables. Look at this thing. What is going on here? Yeah, he just wants to die. I think we're on 33. Whoa. Where are we at? What day are we on? 33? No wonder it looked weird. Thank All right. So let's make sure everyone's following here. If we use this expression, delta G0 is 25 degrees Celsius, 1 atmosphere. That's what the standard means. But let's say they want to know, here's a homework question. This is 25, that's not changing the temperature. Here's one. They want to know what the temperature is at 1,000 degrees Celsius. So that means you have to use your delta G expression. Where it is? Here it is. So the only thing that changes, the T that they give you, plug it in for T, but make sure it's in what units? Kelvin. And then where do you get this? Let's say we're at 1,000 degrees, like that homework question that's coming up. Where do you get the delta H0 and the delta S0? The tables, because you see a superscript 0. So that's what the equations are trying to tell. They're trying to tell you, hey, use the table to get delta H and delta S because they're superscript zeros. Just plug in whatever temperature you're at, and you'll get the delta G at that temperature. Okay, that's what little subscript T means. So it's not that bad to use. Okay, let's just practice a few of these. Give the expression for the thermodynamic equilibrium constant. Oh, I think we skipped something. Didn't we skip? Yeah, we skipped this. I thought we did. How do you solve for K? Right? Because this is where we're at. We're talking about, you get this from the tables. This is when things kind of locked up on us somewhere here. We talked about the R you have to use, the 8.314. The T has to be in Kelvin. So Kenneth, I guess the homework question would have to give you all that information. They have to give you the delta G0, or you calculate it, right, from the tables. You look up the right R to use, the one with joules in it. You get your temperature in Kelvin. And so you get all that stuff in that nice equation. You plug it all in, right? Make sure this guy is in joules, because if you get him from the table, he's in Kelvin. And then you'll have this negative, this number, natural log of K. So how do you solve for that K? Oh, do what first before you do little e? You're on the right track. Yeah, get all these numbers over here. Divide them over. Where's the change color here? Get all these guys down here, right? Bring it over. And now, Kenneth, take both sides to the little e. It's on the calculator somewhere. You just got to find it. Right? Raise both sides to the little e, because e to the ln k, these are inverse functions. They just cancel out. That's just k. Okay. So you have to find the little e to the x button. We'll practice one of those, I'm sure. But let's build up to it. Give the expression for the thermodynamic equilibrium constant. So go ahead and write it. K is, don't write Kc, write K. Products over reactants. And we'll see if everybody agrees. We'll keep going here. So Kendall, what did you put? Yeah. Whoop. You did the bracket things, right? Yeah, perfect. You caught it. This one little trick there. Do the same thing now, everybody, for the bottom one here, for 60. Thermodynamic equilibrium constant. And maybe you've seen how they want you to do this in the book. Maybe you haven't. We'll find out. They don't want you to write brackets, right? Because they're all gases. For a gas, you're supposed to use, have you seen this in the book? they want you to use capital P's because they're all partial pressures. So for gases, use use capital P's. And the little subscript is going to be the compound. So if Enrique, that's the case, what'd you put? Yeah, you'd be saying, well, use capital P. So what would you write on top? Capital P with a, what subscript? Anybody help them out? It's got to be the CH3OH. And not squared or anything. All right? Audrey, you see how to do this? What's on the bottom? Big P, CO. Yeah. You two at the top. You got to square it. Exactly. That's how you. That's what they want you to be doing. Okay. What is a standard free energy change at 25 degrees Celsius for the following reaction? Okay. That's part A. Part B is get a number for K. So he'll finally get to practice your calculator usage. What extra information is given here that you don't even care about? Oh yeah, the liquid you don't care about. Well, if you're going to write an equilibrium constant expression, but you're not, you can get a number for it. What information do you not need? Well, you might need that. I think you're going to need that down here in part B. That table is giving you some extra stuff. All you need, because remember there's an easy way and a hard way to get delta G0? Right? Here's the hard way. It's all there in case anyone wanted to use it. That's the hard way. Use the table to get delta H0. Use the table to get delta S0, right? Subtract those two. Why not just use the table to get delta G0 in the first place? So that's what I'm looking at. I'm saying disregard this stuff. Because delta G0 is products minus reactants. Why go through using this? So delta G0 is just going to be what? That's not even that bad. Negative 108. With what units, though? Kilojoules per mole. The units are going to kill you if you don't keep track of them. Right? Because it's products minus reactants. And then get a number for the thermodynamic equilibrium constant. Start with the equation, right? The natural log expression. Yep. Because it's just 2 times this, products minus reactants. And then minus the zeros. Pretty sure that's how we wrote it, right? Delta G0 is negative RT natural log K. Yeah. Substitute everything in. Just watch your units. See if you can get a number for K. Yeah. Well, what I did is I put a 10 to the third in for the kilo because my joules have to cancel out. So either I got to convert, if I leave this at negative 108 kilojoules per mole, then I better convert R to kilojoules. So that would be 0.008314 kilojoules per mole Kelvin. So you have two ways to go. You just got to get those joules to cancel out one way or the other. So I just chose the easy way. Kilo means 10 to the third, so I just put in 10 to the third for the kilo. Did you get some crazy huge number? No. So first take this no. Do you see how do you see why I wrote? Does everybody see why I wrote 108 times 10 to the third? Because the problem is that R has joules in it. So I got to get this guy to have joules in him. And it really should be written as negative 1.08 times 10 to the fifth. Same thing. So negative 1.08 times 10 to the fifth, or negative 108 times 10 to the third, they're the same number. It doesn't really matter which one you use. But the point is that it has to be in joules, otherwise that joules is not going to cancel with the joules in the R. So I got to convert it. So I ended up with like a 43.59 has to equal the natural log of K. Well, the negatives cancel. Right? Because I've got a negative 108 has to equal a negative 8.314. Because the equation is delta G0 equals negative RT. So my negatives are going to end up canceling out. So now you have to raise both sides to the, you push the what button? Well, let me get it back. 43.59. Okay. To get rid of that ln, I have to raise both sides to the little e. So you got to look on here until you find e to the x. And it's yellow, so that means you have to push shift first, right? So you push shift e to the x. Oh, shoot. 43.59, shift e to the x. I get like 8.5 times 10 to the 18th or something. Somewhere you should be getting around 8.5 times 10 to the 18th. Make sure you get that to work. And it seems odd. When do you ever get answers like this? You almost assume that they're wrong. So it's good to have a feeling for this. Delta G0, we're talking about a reaction. It's a big negative number. Is it spontaneous? Yes. So does that mean when equilibrium is reached, are you going to have a lot of product or very little? It's a spontaneous reaction. It wants to go that way, big time. You're going to end up with a lot of product, a lot. So that means K, which is products over reactants, you better get a huge number for K, and you do. Okay. So come by if you have some questions. We can work on some of these.